Hi guys, Dr. Hasbullah here, and in this video, you're gonna discover how to use the equations that you have derived so far to solve a problem. In this video also, we're gonna find the drag in Lamina region and also in Turbulent region, and what happens if both Lamina and Turbulent are present on the flat surface, and what happens to the drag. So let's start with an example where you have a flat plate. Okay, and you have a flat plate here. And you have a free stream velocity coming from the left. Okay, and the free stream velocity is 5 meter per second. And the length of the flat plate is 4 meter. Okay, so the length here is 4 meter. The width of the flat plate is 5 meter. So you have the length and also you have the width. Okay, and why do we need length and width? Because we need the area. Remember that we found the wall shear stress, right? And you also know that shear stress multiplied with area will give you drag force, right? That's why we need the area. So we need the length and we need the width. And there are two things that you need to find from this problem. First is the boundary layer thickness at the trailing edge. Okay, and what is trailing edge, right? Trailing edge is the edge at where the flat plate ends. Okay, and we have leading edge here and also trailing edge here. So if you have a boundary layer that looks like this, you're basically looking for the thickness at the trailing edge. Okay, you are looking for the del at the trailing edge of the surface. And the second thing that you need to find is the drag force due to the flow on the surface. Okay, so the second one is FD. Alright, now, here's the tricky bit, okay? You are given two conditions, okay? So the first condition, A, is where you are going to neglect the Lamina boundary layer, okay? First, you need to neglect Lamina layer, boundary layer, and the second case, you're going to mix Lamina and Turbulent boundary layer, okay? So second case is Lamina plus Turbulent. And the critical Reynolds number is 5 times 10 to the power of 5. First, we're going to find the del and the drag force for Turbulent only. And B, we're going to try and find what happens to the del and also to the drag force if both Lamina and Turbulent are present on the surface. Okay, let's do A first. Okay, so for A, you're going to need to neglect the Lamina boundary layer. So what happens is that you're going to assume that for the total length of the plate, you only have Turbulent. Okay, this is quite strange, right? Because we know that we usually have Lamina and we usually have Turbulent, okay? But let's say, just to satisfy the problem, okay? So problem A says that we're just going to neglect the Lamina and see what happens to the del and drag force. And to find the del, you simply go back to the equation that you have derived before. Okay, so del is equal to 0.378x divided by Rex to the power of 1 over 5. So 0.378. So del is 0.378 x divided by Rex to the power of 1 over 5. Okay, and what is your x? X is the length of the flat plate. Okay, so it's this length. And this is equal to 4 meters. So x is simply 4. And what you do is just you replace the x. Okay, so del is 0.378 times 4 divided by, and Rex is u infinity times x divided by nu to the power of 1 over 5. And if I'm going to replace everything, this is 0.378 times 4 divided by u infinity is 5 meter per second. X is again 4. Right, divided by nu, and nu is 1.6 times 10 to the power of minus 5 to the power of 1 over 5. Okay, so let's put everything in the calculator. So 5 times 4 divided by 1.6 So minus 5 to the power of 1 over 5. Okay, 0.378 times 4 divided by everything. So you will end up with del equal to 0.091. Sorry, this is 0.09124 meter. Okay, and that is your del. So the distance here is 0.09124 meter. Before we find the drag force, just take a look at the answer, right? The length of the plate is 4 meter. Okay, but you have del at the end. It's just at about 0.1 meter. Okay, so the boundary layer is actually very thin compared to the total length of the plate. So whenever you get the answer, try to get a sense of scale of what's happening. Okay, and now you know that even though we draw the boundary layer as quite thick, but in actual case, the boundary layer is actually very thin, right? So now let's find the drag force. So first we know that CF, the skin friction coefficient, is FD divided by half rho U infinity square L. Right? So FD is CF times 1 over 2 rho U infinity square L. Right? But this is actually the drag force per unit length or the drag force per unit width. Okay, to find the actual drag force, you're going to need to multiply this equation with CF times half rho U infinity square L, and you need to multiply this with the width of the plate. Okay, the width of the plate. Alright, first of all, let's find what is CF. Okay, we're going to find this from the equations that we have painstakingly derived before. Okay, so this is your CF. That is 0.0735 divided by Rex times 10 to the power of 1 over 5. So this is 0.0735 divided by Rex times 10 to the power of 1 over 5 times half rho for air is about 1.2, so I'm going to give it 1.16 times U infinity is 5 square times length is 4 and the width is 5. Okay, and when you put everything together, this is 0.0735 divided by, this is U infinity times X is 4 divided by the kinematic viscosity. This is 1.6 times 10 to the power minus 5 to the power of 1 over 5 times half times 1.16 times 5 square times 4 times 5. Alright, and you will end up with 1.28 Newton. Okay, and that's it, guys. That is your drag force due to the turbulent boundary layer on top of the surface. Okay, so there you go. You've settled case A, which is the del and also the drag force. Okay, so now that we have obtained the boundary layer thickness at the trailing edge and also the drag force, we should move on to question B. But before we do that, let's do some checking. Okay, and if you notice that the power law indicates that N could be 7, could be 8, and also could be 9. Okay, and if you remember, the equation that we've used here is actually based on N equal to 7. Right, so how do we know that we have chosen the correct power law? Okay, let's do some checking here. So let's find the Reynolds number. What is our Reynolds number for the total length? That is U infinity times L divided by nu, which is 5. The length is 4 divided by nu is 1.6 times 10 to the power of minus 5. Okay, and that's going to be 20 divided by 1.6 times 10 to the power of minus 5. Okay, and this gives me 1.26 times 10 to the power of minus 6. Alright, and if we check the condition for using N equal to 7, I believe it's here somewhere. Okay, back to the very beginning of turbulent boundary layer. Okay, so there you go. This is the condition for using n equal to 7, right? And for n equal to 7, right, the Reynolds number must be less than Rex must be less than 10 to the power of 7. And let's see what we found here. So we found here that the Reynolds number is, okay, and this is definitely less than 10 to the power of 7. Sorry, I think I made a mistake here. So this is actually 6. So 1.26 times 10 to the power of 6 is definitely less than 10 to the power of 7. So our assumption is n must equal to 7. So good for us, it means that we have chose the correct equation. If n is equal to 8 or 9, then you're going to have to derive again the equation in order to get a proper terms for del and also the drag force. Right, so now we can move on to question B. Okay, so for question B, is the mix between lamina and turbulent. So here you have lamina plus turbulent. And the critical Reynolds number is 5 times 10 to the power of 5. That's the normal Reynolds number of the transition between lamina to turbulent. Okay, and if I can draw again, only this time the boundary layer is going to look something like this. Okay, you have the lamina and also you have the turbulent. Okay, and in here you have the critical length xc where the lamina shift to turbulent. Okay, if I just label here, this is lamina portion and here is turbulent. And if you remember, our objective now is actually to find the del. Okay, previously we found the del when everything is turbulent, but now we have lamina flow in front of the turbulent. And let's see if the value differs. Okay, and we're going to find del and also we're going to find the drag force. Okay, so to find del, first, you know that del is given in terms of x, right? And you know that you're going to need x, right? Alright, and the del for turbulent, because del here, if you notice, is related to this thickness, right? And this thickness is actually inside turbulent region, right? And if you remember, previously we already have this equation. So del is actually 0.38, is it 0.38? Sorry, 378 times x. So 378 times x divided by Rex to the power of 1 over 5. Okay, now the only thing that we need to find out in order to find del is x. Okay, previously in part A, we can use x equal to 4. Okay, because we said that there's no lamina. But now when you have lamina, you're going to need to find the new x, right? So that you can solve this equation, right? And to find the x, okay, let's draw the imaginary origin of the turbulent boundary layer. Let's say turbulent boundary layer starts from here. Okay, it starts from here, right? And this x is going to be the distance from here to here. That will be your x that you're going to put in here. Right, now the question is, how do we find that x? Right, first of all, you need to find xc. Okay, what is your critical transition point? Right, and to find xc, you have the reference, which is the Re critical, Reynolds number critical. So Reynolds number critical is equal to U infinity times xc divided by nu equal to 5 times 10 to the power of 5. Okay, and to find xc, it's very simple. So 5 times 10 to the power of 5 multiply with the kinematic viscosity, multiply with the kinematic viscosity, that is 1.6 times 10 to the power of minus 5, divide by U infinity is 5. Okay, and you'll end up with XC equal to 1.6 meter. Okay, so XC is 1.6 from the leading edge of the flat plate. Okay, and now that we know that this is the del at that point. Okay, so at XC, this is the del. Okay, and this is del for both lamina and turbulent. Okay, and when we know XC, meaning that we can find the del because we already have X. So to find the del for lamina, we're going to take a look at our previous notes. Okay, so let's go. So del for lamina is equal to, so let's do del for lamina. Okay, it's quite further back, I believe. It's going to be 4.65 x divided by Rex to the power of half. Okay, and this equation we obtain by using the cubic equation, right? So by using the cubic equation, we got this, right? And now we're going to use it. So this is 4.65 x divided by square root of Rex, right? Now you can use this value, right? You can definitely use this value, okay? But when they did the experiment, okay, someone else has done the experiment and they found out that the better value is actually 5. Okay, so just to use the better value, alright, so we're gonna replace that with 5. Now remember, it's still okay if you use 4.65, right? It's just that the better value that they found from experiment is 5. Okay, there's nothing wrong with using 4.65, but I want to demonstrate what is the answer if you use 5. Okay, so now let's do here. So 5x divided by square root of Rex. That will be 5 times x. Our x is 1.6. Right? Divide by square root of Rex is U infinity, which is 5 times x is 1.6. Divide by 1.6 times 10 to the power of minus 5. And for this, you will find the value of del. Right? Let's find it. So this is 5 times 1.6 divided by 1.6. 10 to the power of minus 5 square root 5 times 1.6 divided by everything. And you will end up with del equal to 0.0113 meter. Okay, so del here is 0.0113 meter. Remember, we are looking for del here. Okay, we are looking for this del instead of this del. Right, so this del is just for reference now. Okay, and if you notice, this is the point where del for lamina is equal to del for turbulent, right? Because the point of lamina and turbulent intersect here. Okay, now why is it important? Is because you know you have the relationship between del and x, right? So when you have x, you can have del. And when you have del, you can have x, right? Now, what you've done is basically you already have del, right? And if we equate this with the turbulent equation, you're gonna get x for turbulent, okay? And you are going to get the value here, right? We need that because in order to find this here, okay, we need this value, right? Okay, so let's try and find it. And for turbulent, so del turbulent, and we've done this before. This is, I think, 0.38. Okay, 0.378. 0.378x divided by Rex to the power of 1 over 5. Right? But now we already have del. Del is 0.0113 equal to 0.378x divided by, the velocity is 5 times x is something that we are looking for. So this is x divided by 1.6 times 10 to the power of minus 5 to the power of 1 over 5. Okay, now this is where I need you to be very careful when using your calculator, because it's very easy to make mistakes simply because you forgot that the x here is to the power of 1 over 5. So please don't make that mistake. Okay, so what I'm going to do is that I'm just gonna divide this first. So I'm gonna end up with, this is x to the power of 4 over 5, right? And I'm gonna take everything out of the bracket. So 5 divided by 1.6 to the power of 5, 1.6 times 10 to the power of 5, and everything to the power of 1 over 5. Okay, and then 0.378 divided by everything. So you will have here equal to 0.03x to the power of 4 over 5. Now, can you find x now? Of course you can. So let's do x is equal to 0.0113 divided by 0.03. Okay, and everything is to the power of 5 over 4. And you'll end up with x equal to 0.295 meter. And depending on how many numbers you take, so this might differ. So it might be 0.25, it might be 0.292, 293, 294, 295. It doesn't matter, right? As long as the answer is close enough. So x is 0.295. And where is this x? So this x is here. Okay, this is 0.295 meter. Okay, now that we have found that, right, I'm going to label this xt. Okay, xt. So t is for turbulence. So xt must be equal to 4, which is the total length of the flat plate, okay, minus 1.6 plus 0.295. Okay, that will be my xt, right? So my xt now is, I'm just going to write it here. So 4 minus 1.6 plus 0.295, that is 2.695. That will be my x turbulence. Okay, now with that x, can you actually find this del? Right? Can you actually find this del? So definitely you can. So del is equal to 0.378 times 2.695 divided by u infinity is 5 times 2.695 divided by 1.6 times 10 to the power of minus 5. Okay, and this will become your actual del. Okay, and I may run out of space here, so let's write everything here. Okay, so del is this is to the power of 1 over 5. Okay, and let's do the calculation. So 5 times 2.695 divided by 1.6 times 10 to the power of minus 5. Everything to the power of 1 over 5. 0.378 times 2.695 divided by everything. You will find that your del is 0.065 meter. Okay, so del here is 0.065 meter. Okay, so that's how you find del when you have lamina and turbulent boundary layer. And before we compare this with case A, alright, let's just carry on and find what is the drag force is first. Okay, so drag force for lamina plus turbulent. So from the equation, we already know that FD is equal to CF times half rho U infinity square LW. Alright, and this term is actually very similar with case A, but the only difference is your CF. Okay, now that we have a very prominent laminar and turbulent region, so the suitable CF is this equation. Okay, so CF is now equal to, let's do this. So CF is equal to 0.073 REL to the power of minus 1 over 5. You need to subtract this with 1700 RE to the power of minus 1. Okay, that's how you find the CF. And this is where it differs from the case A. Okay, so CF is simply 0.073. REL is U infinity is 5 times X is the L is 4 divided by nu is 1.6 times 10 to the power of 5 to the power of minus 1 over 5 minus 1700. RE is again 5 times 4 divided by 1.6 times 10 to the power of 5 minus 1. Okay. And this is equal to 4 divided by 1.6 times 10 to the power of minus 5 to the power of minus 1 over 5 times 0.073 minus 1700 times 1.6 times 10 to the power of minus 5 divided by 20. That is 3.045 times 10 to the power of minus 3. And now it's time to find the FD is 3.045 times 10 to the power of minus 3 times half. Rho is 1.16, U is 5 square times length is 4 and width is 5. Okay, so by 2 times 1.16 times 25 times 20. Okay, so you will have here the drag force is 0.88 Newton. Okay, so there you go. So del is 0.065 and the drag force is 0.88. Okay, now let's compare, okay, between case A and case B. So for case A, right, and case B, right, so del for case A is 0.09124, 0.09124 meter, and the force is 1.28 Newton. Okay, and for case B, the del is 0.065 and the FD is 0.88 Newton. Okay, and if you remember, A is when we assume everything is turbulent and B is when we assume you have laminar and turbulent. Okay, now see the difference here. Okay, at first, let's see the difference of del. Alright, so obviously here, you can find that if you simply neglect the laminar, right? If you simply neglect the laminar, you're gonna have the value of del which is thicker than the actual value. Okay, of course, you know that in any case you will have laminar and turbulent, right? So if you neglect laminar, you have the risk of overestimating the del. Okay, and also you have the risk of overestimating the drag force. Okay, now here is quite significant because this is about 45% smaller. So the actual case, which is case B, is actually 45% smaller than case A. So that's quite a very big difference between when you assume there is no lamina and when you have lamina and turbulent. So you need to be careful and analyze the question whenever you get it. And in the real world as well, make sure you are fully aware of what's happening before you try to analyze it. Right? And as you notice that even though it's a very long step, okay, you have to determine the velocity profile, and then you have to derive the drag force, and then you have to find the suitable solution that fit into whatever problem that you have. But even though it's complex, even though it takes very long, right, the path is there. As long as you keep repeating it, you will know how to do it, even with your eyes closed. But the problem is, right, you need to understand the problem. Okay, you need to understand the issue. You need to understand the question. Okay, it's more difficult to find out what to calculate rather than how to calculate it. Because how to calculate it is quite simple. You already have the equation. But what is it that you want to calculate? That is, of course, quite difficult. And with practice, you can definitely do that. Right? So keep working on the problems and eventually you'll find this thing very easy. So keep repeating this example and do it over and over again. You can replay this video as many times as you like until you understand it. Okay, so thank you very much. I'll talk to you soon. Bye.